Good morning, everyone. So, as I said, I'm Roger Sacilotto. I work for Avid, and we contracted with Ancora to work on a project that we were interested in investigating, which is how to use large language models and knowledge graphs to improve news production. So why would you want to do something like that? So typically, the way people search for things is they take their content and put it into a search engine, say Elasticsearch, and then they can query on things. And the results of the query really depend on how well your indexes are created and the quality of the content is in terms of whether you've got structured data in fields and you're able to make the right field queries to find the exact right stuff. So LLMs offer a little bit of improvement because, as we've seen, they can offer a more conversational way of interacting with data. But that means that you have to make your data, work with the LLM. Typically, news stories are current. LLMs are trained with data that is not. And so you have to basically add your content to the LLM in order to get a reasonable output. And that is something typically used. There's a technique called retrieval augmented generation, where you've got this giant set of data and you want to get some of it into the LLM for a particular query because they are limited. They can't handle everything that you might want to throw at it. RAG or RAG is a technique where you take all the content, you break it up into chunks, you index those chunks, creating embeddings, and then you compare your query embedding, your similarity check, with the database of indexed embeddings, and you get some chunks back. You get some objects that you can then say, okay, I'm going to add these to my query, and now the query will run on those objects. The problem with that is that LLMs have limits. You can't put everything you want, so you really have to pick the most relevant things. And that's where we kind of bring in knowledge graphs, is we want to see if that could do a better job of finding the most relevant things. So I'm going to go through a little bit of a very, very hyper simplified example of what this might look like. So as a basic level, graphs have nodes, which represent entities or things that are either in a computer space or in real space. And then there are edges, which relate. They're directional relationships between one entity and another. And entities can have properties. And if you use a labeled property graph, even the relations can have properties. So let's say we're working on a story about the Supreme Court, United States Supreme Court. So the Supreme Court would be an entity in a graph. And the Supreme Court has justices. They would be entities, and there would be relationships linking the justices to the Supreme Court. And as I said, you can have properties on the relations, and they could, for example, indicate their term. When were they active justices? And then there's cases. They decide cases. That's what they do. These cases often come from district court rulings, and they're brought to the Supreme Court by a petitioner. So we have these graph nodes and relations. The relations have semantic meaning. They're not just arbitrary connections. So the connection between justices and cases is that they wrote the majority opinion for that case, or that the case originated in a district court, or the case was brought to the court by a petitioner. Okay, so we have this information. What's valuable about it, especially to a business, is these graphs can be accumulated over time. Stories, you have one story in 1 year, a couple stories in another year. Those get added, and it accumulates the amount of knowledge that you have about the entire news domain around this area, or even extending into all your other areas. So you can just keep growing your knowledge as you acquire more information. These, again, the relations are very specific. And so you can use that as part of your queries to make sure you know exactly what you're looking for. And patterns in the graph can allow you to sort of infer meaning where it might not have been known otherwise. So if you look at this graph, for example, you're working on case 2. In case 2, first thing you can notice is that it was the opinion for that was the majority of opinion for that was written by Justice Y. Now, Justice Y also looked at wrote the opinion for case 3 and 4. I have a typo here. I have 2 4s, but there's a 3 and a 4. If you're looking at it from the point of view of the district court, the 5th district originated this case 2, but it also originated case 1 and 3. And finally, this case was submitted by a petitioner who also was submitted 1, 3, and 4. So if you want to look at the connectivity of these objects, you can maybe come up with some patterns here that says, well, if I want to know what objects I want to send to the LLM, I might want to looking at what the most connected relationships are, which could bring me to, okay, let me pull up 3 and 4 because of the connections to a specific justice, or 1 and 3 because of the connection of the district, or 1, 3, and 4 because of the connection of the petitioner. But, by looking at these communities or strongly connected groups of objects, you can make decisions about, what do you want to pull from the graph and bring into your model. And then that can make what limited information you can pass to the LLM the most relevant for whatever priority that you have when you're looking for information. And then all this can be linked to media so that you can now have the access to any sound or video footage that you want to bring in and use based on the results of these queries. So what's difficult about this? The knowledge graphs look like they're great, right? Well, creating them is not easy. If you try to do it manually, if you try to have a person look through the documents, identify the objects, create entity IDs for them, make sure they don't do duplicates. You don't want to have, the same entity represented multiple times in the graph. That makes life more difficult. You don't want to have different relationships that are the same thing. Again, keeping things that are semantically coherent gives you better results. So at scale, it's very, very difficult, if not impossible, to build this as a manual activity. So what are we looking at? There is a lot of research around looking at unstructured text and turning it into a graph. So Ancora did a bunch of research. We used 3 actual news stories to test the techniques, created a graph. One very important thing is we connected the entities to an external source, which is Wikidata, which gives you a lot of value. You don't have to bring in all that external information into your own database, making it larger. You can just reference it, and if you need it, then it's very easy to go and fetch it through, say, for a Sparkle query to Wikidata. And then finally, we took that information, and because it was very small, we just basically created, we dumped the text out of the database and indexed it and ran the LLM on that. And we're able to ask it some questions and get some relevant answers. Again, that was just for us to complete it, but it's not the real RAG pattern, but it's saying if this was the result of the query, then we could get some meaningful answers to some decent queries. Anyway, that's it for me. I'm going to have Caio come up and talk about the actual good stuff in this talk, which is how his experiments went in terms of looking at unstructured text and generating graphs.
Thanks, Roger.
Just push the move button. Yes.
Okay. So, as Roger mentioned, one of the key points of our solution, is the knowledge graph. So now I will walk through our solution to create this knowledge graph from unstructured text. So just giving an overview of the solution. So we start with unstructured text. Then we will detect the original language of this unstructured text. And then we verify if this language is English or not. If it's English, we then create the knowledge graph. It's not, we then translate to English to create a knowledge graph. And we did that because one of our concerns during the implementation of this solution is to ensure that the solution is reliable against different languages. So we decided to work all the process in English and just translate the original text to English when they are not. And during the knowledge graph creation, we also enrich the knowledge graph using the Wikidata information that we collected from the internet. And once we have this knowledge graph enriched by the Wikidata information, we then persist this knowledge graph into a graph database. And in our case, we use Neo4j to do that. Okay, about the technologies, for these two steps for language, we use interaction with large language model. And now let's talk more about the process behind the knowledge graph creation. So basically, this process were done dividing by 3 different procedures. And we did that to avoid reduce the influence, the impact of the hallucination of large language model during our process. And we also did that to reduce the complexity to create knowledge graph. So basically this process are composed of 3 procedures. The first procedure is the candidate triplet extraction. By triplet, I mean any type of a connection between 2 entities. And then we pass through another procedure called object resolution. The object resolution is responsible to disambiguate these triplets that we defined before. And then we create the taxonomy related with the classes associated with the entities that we defined during the candidate triplet extraction. So basically, after the object resolution, we then create our knowledge graph. And after the taxonomy inference, we define a taxonomic hierarchy that establishes the relationship between the classes that we have into our knowledge graph. And putting both together, we then can define a domain ontology. We call it domain because we are looking for one text, so only for one unstructured text. So this domain is related with this text that we are processing and input. So let's talk more in depth about the candidate triplet extraction. This procedure were made by many different steps, starting with the extraction of the entities and their classes that can represent these entities. Once we have these entities and the classes, we then define the descriptions associated with the entities. It's important to notice that the descriptions should be represent the main whole of the entity in the input unstructured text. And once we have the entities, the classes, and the descriptions, we then identify which of these entities are named and which not. By named entity, we mean any type of entity that can be recognizable for different domains. So normally, named entity could be personalities, politicians, countries, institutions, and others. And once we define these named entities, we then apply more steps, but now for each of these entities defined before. So for each of these entities, we then first, when we have a named entity, we define a more broad description for this entity, and then we will recognize the other entities that are mentioned in the description of the entity under consideration. Once we define these mentioned entities, we then define the possible relationships that we can establish between the mentioned entities and the entity under consideration. And once we have these relations, we then define the descriptions for each relation that we have. So after all these steps, we then can define our possible candidate triplets. And candidate triplets could be defined as 2 sets, one set for entities, classes, and their descriptions, and other set composed of relations and the descriptions. About the technologies, most of the steps we use large language model interaction, with the exception of the identification of the entities and the description. We use it for this specific step, the simple regex to define that. In next, after to get all these triplets, we then do the process of object resolution. By object, we can understand any type of object that we have into our knowledge graph. So entities and relations. So the first thing to do here is to create some types of aggregations that take into consideration the semantic of these objects. And we do that. When we do that, we then create some clusters. And once we have these clusters, we then use another procedure to disambiguate the elements that we have for each cluster. And once we do that, we then create a global concept for each cluster that we defined before. Once we have this global concept, we then can mapping the global concept with the elements of each cluster. And then we create this disambiguation of the objects that we had, and then we can create our knowledge graph based on the final triplets that we collected after this procedure. About the technologies, we use large language model for cluster disambiguation and cluster concept shrinkage. And for aggregation, we use a combination of BERT and ADB scan. BERT was used to create a vector space, and ADB scan was used to define the clusters into this vector space that we defined using BERT, applied to the labels and the descriptions of the entities and relations. About taxonomy inference, the procedure is very similar to the last one, but now we are focused on the classes associated with the entities that we defined before. So we apply the aggregation over the classes, and once we have the clusters of classes, we then define a hypermean for these clusters, which means that we will define a more generic concept that can represent all the classes for each clusters that we defined before. So once we do that, we will check how many clusters that we have. If we do not have one cluster, we then repeat the process until we have just one cluster. With this procedure, we then create a tree that can go for from a more detailed class into a more global representation of the class, creating our taxonomy hierarchy. About the technologies, we also use BERT and ADB scan to make the aggregation and large language model to create the hypermean. Lastly, let's talk just quickly about how was made the integration with Wikidata. This integration was made only over the named entities, because we understand the named entities, the key points that can create the connections between different stories. So using the labels and the broad description associated with named entities, we then define a SparkQL query that is responsible to interact with Wikidata. This SparkQL will retrieve a table with all possible matches from Wikidata that can be matched with our named entity. And then we will define the best match. Once we have this best match, we will collect any one hop neighbors of this best match entity from Wikidata. And to do that, we also use another SparkQL query. And once we have this any hop neighbors, we then define a subgraph. And with this subgraph, we then can merge with the original knowledge graph that we extracted from the story. Okay, so this is basically our solution. About the technology here, we just use BERT during the best match, because we needed to create the vector space and then analyze the similarity, the distance similarity between the possible matches and our named entities. Okay, so once we finish this solution, we then recognize some points that can be improved. We can extend the integration with external sources. we can also investigate more about possible graph metrics like betweenness, PageRank, and clustering, or graph neural networks techniques to improve the information retrieval from the knowledge graph. And we also can investigation a way to work with another type of data like metadata, image, and audio. So now Roger will.
Thanks, Caio. Okay, so to wrap up, find out where I'm looking at the slide here. So the last thing we did, this is just something to put in a demo, that we took the proof of concept approach where we generated the graph. Instead of doing something a little bit more dynamic, because there was so little data, it was easy enough just to extract the data, generate embeddings and load it into an index and use that as context for a chat. Again, as future approaches, we want to do a little bit more with embeddings more closely related to the data, and use different techniques to find similarities. And again, as Caio mentioned, doing some other sort of cluster analysis to find things that are nearby that represent interesting areas that go with the original context. So ultimately, the proof of concept, we were able to generate the graph, and we had the entities were disambiguated. It worked really well for that. And we're able to use that data to work with an LLM to give us good answers to some queries that we made. But a lot of work is needed for this. And ultimately, as mentioned before, Kylie said this stuff is changing so fast. This was done over a year ago, and I'm sure that there's some dramatic changes even then. For us, this is not about the AI specifically. It's really about the goal of making the information in the newsroom more accessible to journalists and producers. And how that happens under the covers is less important as to opening up a lot more avenues of inference and insight into the data, making things surface that might not have been known in any other way, and using the knowledge graph to aggregate all this data and make connections between it seems to offer us a good way to do that, regardless of the specific technology to create it or access it. But anyway, that's our talk. So thank you very much.
Thank you so much. Do we have some questions? We have a couple minutes. We can dig. Oh. Okay.
I was curious, it looked like from the presentation that you guys were inferring sort of the graph ontology from your data. Yeah. I was curious if you actually tried using a pre-known ontology and trying to map the data into that ontology instead.
One of the discussions we've had is using a sort of pre-cooked ontology as an input to the disambiguation process and steering things towards that kind of, having something that we've already been defined previous to the collection. In the absence of that, the first in will sort of set the stake, and then everything else will hopefully cluster around that.
Thanks. Yeah, when we've tried it, seems like it actually works better to let it infer the collection rather than trying to map to an ontology. It seems to struggle. The LLM struggle with that. So yeah, I'd be curious if y'all make any progress.
Well, I don't think we've really done so much since this project, but it is a big concern. Huge concern for me is the complexity of the graph and actually putting the information in a way that you can leverage, right? Yeah, I can write cipher queries to do all kinds of incredible things, but that's not going to work in a real setting. So having that set of semantic entities that you can then use tools to navigate and get good answers from is going to be quite a challenge. But I think it's going to be key to making this information or meet the promise of how to leverage it and get the value out of it.
Great. Any other questions right now? I had one. This is not for that way. This is early career day, so there are probably some students in the audience, and you mentioned this is about making information more accessible in the newsroom. How do you think that's going to change how people are being trained in journalism? Are they going to be relying on summarizations? And do you think this is just going to be part of what we expect? And how soon do you think that'll happen?
I still think it's a ways out, at least for Avid. We still trying to, this is in sort of investigation phase. But ultimately, like anything else, prompting is going to make a big difference. Asking the right questions and getting into the detail of that, training people on how the conversation can be best made, will help. And also how to indicate what your angle is. So, finding the right clustering, the right vector to extend or to expand in order to find stuff that may help you, like, find a bigger story, right? So if there are some things like, what look like unrelated stories could mean that, okay, well, when you really look underneath it, there is some meaning here, like this, you expose some sort of mysterious cabal of people that are trying to take over the world, but something like that where I know that there's been some work done in trying to find themes across stories and breaking things down into, like, the prodigal son, where you have someone that has gone away and come back, and there's stories around that you can factor. So just because there's a story about someone who did something, all of a sudden you say, well, wait a second, that person came from this city and they attended school here and they were doing some work and we reported on that earlier. Now let's follow that up and say, look what's happened with them downstream. You might not have known if you didn't make that connection of their earlier work.
Great. Awesome. Well, we have one more.
So just following on what Kylie was just asking, for students, do you think that students really need to investigate AI tools, AI programs, and so on, because either it will impact what their jobs might be, or because they may be expected to use these kind of programs in their work?
We honestly haven't been looking at that angle of it, so I couldn't say. It's really about after the fact discovery more than sort of anticipating how to do things differently to get a better downstream result. So.
Excellent. Well, thank you both so much.
Okay. Is there one more? Well, I don't, if we're out of time.
If you make it fast. If I can run to you fast. There we go.
No, I'm sorry. I just, actually for students, I notice, that Neo4j, I mean, you can learn it. They have all the tools online. It costs nothing to learn Neo4j. If you're interested in graph databases. But my question was, there are several options out there for building those kind of models and building a graph database. And I just wondered how you guys chose Neo4j as the back end for this.
So yeah, I've been working on graph databases for like over 10 years. And Neo4j, first of all, I love Cypher. So that was a big influence on me, as opposed to, say, Gremlin. Sparkle's okay too. But anyway, it just works. It's a really good system. They've got a lot of investment going into data science and hooking into AI, and they've got vector indexes. So it seems like it's well positioned for the kind of work we're doing.
Great. All right. Thank you so much, Roger and Caio. Give them another round of applause, please.